Hello, I am Elena and I will be talking about the history of Brooke Taylor. So I will first be talking about Taylor's general timeline. I'll be getting into the specifics of these events in the upcoming slides. So first, Brooke Taylor was born on August 18, 1685. In 1701, he entered St. John's College, Cambridge. Then, in 1708, he wrote his first important mathematical paper. However, this wasn't published until 1714. And in 1714, Taylor was elected as secretary in the Royal Society. A year later, Taylor formally introduces the Taylor series. Lastly, he passed away in 1731. Brooke Taylor was born in Edmonton, England. Taylor's father was John Taylor, and he was a member of Parliament of Patricksburn, Kent. Taylor's grandfather, on his father's side, was Nathaniel Taylor. He was a recorder of Colchester and a member representing Bedfordshire in Oliver Cromwell's assembly. On the other hand, Taylor's mother was Olivia Tempest. Her father, or Taylor's other grandfather, was Sir Nicholas Tempest, and he was the Baronet of Durham. This is just the general family tree of Brooke Taylor. As you can see, Brooke Taylor's father and mother are John and Olivia. I mentioned Nathaniel and Sir Nicholas Tempest previously, which are Taylor's grandfathers. And Taylor's grandmothers are Matilda Taylor and Isabel Tempest. Now for Taylor's education. His father was actually a strict disciplinarian, but was also someone who was interested in the arts. So while he may have had some negative influence on Taylor, he also was able to cultivate Taylor's musical and artistic talents. Not only did this allow Taylor to become an accomplished musician and painter, but both his musical and artistic influences were found in his mathematical expressions later in his life. Since Taylor's family were fairly wealthy, they were able to afford hiring tutors for Taylor. He was actually home tutored all the way until he entered St. John's College, Cambridge. There, he studied law and completed his Bachelor of Law degree in 1709 and his Doctor of Law degree in 1714. However, it is unlikely that he ever practiced as a lawyer. Instead, Taylor was highly involved in mathematics and studied under John Machen and John Keill. Machen is an English mathematician and astronomer, best known for formulas he invented to calculate pi. On the other hand, Keill was a Scottish mathematician, natural philosopher, and an important defender of Isaac Newton. As Taylor continued to pursue his interest in math, he made many contributions. As mentioned before, Taylor wrote his first important mathematical paper in 1708. So this was actually before he even completed his Bachelor of Law degree at Cambridge. The paper was a mechanics paper which rests heavily on Newton's approach to the differential calculus. It obtained a solution to the problem of the center of oscillation of a body. So, even though it was written in 1708, it was actually published in the Philosophical Transactions of the Royal Society in 1714. This delay in publishing actually caused a priority dispute with the noted Swiss mathematician Johann Bernoulli. Taylor also published a famous investigation of his in 1714 on the vibrating string, which included in the volume of the Philosophical Transactions. It introduces pendulum conditions, which state that all elements of the string are supposed to undergo small vibrations as simple pendulums all of the same period. Hence, they are restored by harmonic forces of the same intensity. So overall, this actually played a large role in clarifying what mathematicians meant by a function. Taylor published Methodes Incrementorum Directa et Inversa, also known as direct and indirect methods of incrementation, and linear perspective in 1715. They added a new branch to higher mathematics, which is now known as calculus of finite differences. Among the many finds in Methodes contains an explanation of the process of expanding functions into infinite series and the celebrated formula known as Taylor's theorem. However, this was actually only recognized until 1772, when the French mathematician Joseph Louis Lagrange realized its importance and proclaimed it the basic principle of differential calculus. On the other hand, linear perspective and another work of Taylor published in 1719, New Principles of Linear Perspective, contains the first general treatment of the principle of vanishing points. These volumes were among the final contributions to mathematics before Taylor turned to the study of theology and philosophy. Overall, these works are very important to the history of mathematics and is the reason why it established Taylor's reputation as a mathematician. So, some background on Taylor's theorem. There were actually two versions of Taylor's theorem. While people nowadays would say that they are identical, the authors behind these two versions would argue that they are differently motivated. Taylor's version fell into a general method of applying Dr. Halley's extraction of roots to all polynomials. The second version is thought of as a method of expanding solutions of fluxional equations in infinite series. Assume that Taylor was the first to discover this theorem. There have been other mathematicians such as James, Gregory, Newton, Leibniz, Johann Bernoulli, and de Moivre, who have all discovered variants of the theorem independently, like Taylor. The term Taylor series was actually coined in 1786 by Swiss mathematician L'Huillier. Some general life and family of Brooke Taylor. He was elected as a Fellow of the Royal Society in 1712, and then he was later elected as Secretary in 1714. If you don't know, the Royal Society is a society founded in 1660 to bring together leading scientific minds of the day and became an international network for practical and philosophical investigation of the physical world. Anyway, Taylor had to resign in 1718 partly due to health reasons, but also because he was not interested in the rather demanding position he had obtained. During his time in the Royal Society was when he was most productive in mathematics. Taylor also had to visit France several times due to his health, but also to visit some friends he met. He met Pierre Ramond de Bonnemort. They would converse about various mathematical topics. Taylor married his first wife, Miss Bridges of Wallington, Surrey, in 1721 at the age of 36 without the consent of his father. This actually caused an strained relationship between them. Taylor's wife passed away while giving birth to their son, who also didn't survive. After the tragedy, Taylor returned to live with his father, which repaired the relationship between them. Taylor married again, but this time with his father's approval, to Sabetta Sawbridge of Ollantay, Kent, in 1725. Unfortunately, Taylor's father passed away 4 years later in 1729. Taylor was able to inherit his father's estate of Biffons. Then, in 1730, Taylor was heavily affected by the death of his second wife, who had also passed away during childbirth. Luckily, though, his daughter, Elizabeth, survived. Less than 2 years later, Taylor himself died on December 29, 1731, in London at the age of 46. And that is all. Thank you.
All right, so let's first talk about what a Taylor series is. So in math, the Taylor series of a function is an infinite sum of terms that are expressed in terms of the function's derivatives at a single point. So here's a small example that I have over here. And as you can see, it is just basically a polynomial with an infinite number of terms. And it is also about a certain center point, which I represented as C over here. So what can we do with the Taylor series then? Well, it's commonly used to approximate a value about a certain point for a function. So let's say we have the function e to the x, which would be approximately be like that. So let's say that this is e to the x. And let's say we want to find a value near a certain center value. So let's say the center value is 0, so just the center over here. And let's say we want to approximate a value somewhere around it, like here. So we can use a Taylor series to find a value that's extremely close to this value of the original function. So the first term over here would be kind of like a line over here, and the second term would make it a line like this, and then the third term would make it into a quadratic like this, and then the fourth term would make it like this. And for each term that we add, what we're essentially doing is getting closer and closer to the original function, as you can see like that. So let's move on to Desmos and see what it's like in a real example. So here we have the example e to the x and a bunch of Taylor polynomials of e to the x, each with an increasing number of terms. So let's turn on the first term, which is just a line like I showed before, and the second term makes it so that it is a line along the derivative at the center point 0. And then add another term, we have kind of like this quadratic parabola over here that, as you can see, is getting much closer about the center over here. And let's add another term, and as you can see, we're getting really close to what e to the x originally was about the center. Let's add another term, and as you can see, it's pretty much almost the same, just in this general area. So as we saw in Desmos, the polynomial with an increasing number of terms had a greater accuracy to its original function. So using the same example, e to the x, the Taylor series is shown over here. It is basically an infinite series or infinite series of terms that are added together to make a never-ending polynomial, basically. So since it's infinite, it would be infinitely close to the original function. So how do we find this Taylor polynomial then? Let's continue using this e to the x as an example and find its Taylor series. So let's set this equal to f of x. All right, so the assumption is that if this f of x is infinitely differentiable, then we can convert it into something like this. So a sub 0 plus a sub 1 plus times x minus a center plus a sub 2 times x minus the center squared plus a sub 3 times x minus the center cubed, and so on and so forth. But since we're setting the center as 0 for this example, we can just get rid of this minus a part since it's just subtracting 0. So now we would have something like this. Now to find the first value, we can plug in our 0. So f of 0 is equal to e to the 0, which is equal to 1. And since we plugged in 0, all the terms with an x will just disappear. So we'll be left with f of 0 is equal to a sub 0, which is equal to 1. So we found the first term. Now for the second term, what we can do is find the derivative of this original function. So we would find the first derivative, and then because we're finding the derivative, this would disappear, and it would just be a sub 1 plus 2 a sub 2 x plus 3 a sub 3 x squared plus 4 a sub 4 x cubed plus, and so on and so forth. Now let's plug in 0 again into the derivative. Then it would still be e to the 0 since the derivative of e to the x is equal to e to the x. And this also equals 1. So we can find that a sub 1 is equal to 1. Now let's do this a couple of more times. So f double prime of x, so the second derivative is equal to 2 a sub 2 plus 3 times 2 times a sub 3 x plus 4 times 3 times a sub 4 x squared, and so on and so forth. And we put in 0 in here again, which is e to the 0, which is equal to 1. So now this time, it's 2 a sub 2 is equal to 1, making a sub 2 equal to 1/2. Now let's do this one more time. So f triple prime of x is equal to, now as you can see, there's sort of a pattern over here. It's slowly becoming factorials of its original power on the x. So we can just say 3 factorial times a sub 3 plus 4 times 3 times 2 times a sub 4 x plus so on and so forth. And then if we plug in our center value here, we would get e to the 0, which is equal to 1 again. and 3 factorial times a sub 3 is equal to 1, making a sub 3 equal to 1 over 3 factorial. Alright, so if we keep continuing this pattern or this process, we would find a pattern that a sub n is equal to 1 over n factorial. So if we plug this back into what we assumed in the beginning over here, then we would get e to the x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so forth infinitely. So this is the Taylor series, which can be also written as a summation or a sigma notation of let's say and starting from 0 to infinity of x to the n over n factorial. So this is the Taylor series of e to the x about the center of 0. So here are some other examples of Taylor series about the center of 0 for other common functions. And as you can see, the Taylor series of e to the x about the center of 0 is the exact same as what we just found earlier. And eventually, Brooke-Taylor kind of found a pattern or a general formula for a Taylor series of a function that is infinitely differentiable. And that is f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a to the 3rd power plus and so on and so forth, repeating the pattern infinitely, which is also represented as, in the sigma notation, from n starting to 0 to infinity, we add the following terms over n factorial, all multiplied by x minus the center to the nth power. So this is the formula that he came up with. And in this case, f to the n of a, this is equal to, or this denotes the nth derivative of f evaluated at the point a. So a is the center that we set. And for these Taylor series that we see over here, since we're using the center of 0, we don't really see this part. But if we find it at, let's say, the center of 2, then this would be x minus 2 to the nth power, and we would see a slightly different series. And yeah, so that was how you find a Taylor series for an infinitely differentiable function.
I'm Landon, and I'm going to be talking about the Maclaurin series, the Lagrange error, and some applications of the Taylor series. So if the 0 is the point where the derivatives are centered, a Taylor series is also called a Maclaurin series. It's named after Scottish mathematician Colin Maclaurin, who made extensive use of this special case of Taylor series in the 18th century. Here is a general Taylor series formula centered at x equals 0. Several different Maclaurin series exist for different functions of x. Some notable ones include the trigonomic functions and their inverses, as shown. There is the exponential function e to the x, the natural logarithm ln 1 minus x and ln 1 plus x, and the geometric series 1 over 1 minus x, and so on. Moving on to the Taylor series error, we know that Taylor series is used to approximate functions, which means that there's a disparity between the actual value and the approximated value. It's desirable to have some idea of the size of error you introduce. The error of an approximation of a given function f can be represented as f of x minus Pn of x equals Rn of x, where n is the number of terms in the series. This is known as a truncation error. Every truncation splits the Taylor series into two equally significant pieces, the Taylor polynomial Pn of x that gives us the approximation, and the remainder, Rn of x, which introduces the size of the error. The Pn of x Taylor polynomial ends at the nth term, and the remainder, Rn of x, starts at the n plus 1th term. To visualize what the error bounds of a series are, let's approximate the error of the series 1 over n squared from the 4th term using a comparison test with integrals. If our approximation of the series itself is the sum up to the 4th term, our error is the sum starting from n equals 5. To estimate the sum, I'll use the definite integral 1 over x squared from 4 to infinity. Represented by the graph, we know that the infinite series starting from n equals 5 is less than the integral of 1 over x squared starting from 4. In this scenario, the graphical representation of the series is a Wright-Raman sum approximation, which is an underestimation of the area under the curve of 1 over x squared. This can be shown in this inequality, which then we can solve the inequality by substituting the infinity sign with b and finding the limit as b approaches infinity. Then we find the antiderivative of 1 over x squared, which is negative 1 over x. We plug in b in the 4, so then it solves, and we get 1 over 4, which means that if the sum up to the 4th term of the series 1 over n squared was used to approximate the infinite sum of the series, we know that the error must be less than 1 over 4. Because the series 1 over n squared is convergent, we can find the absolute error of the series to verify if it's within the bound we established earlier, less than or equal to 1 over 4. If we calculate the sum of the series, it comes out to pi squared over 6, which is roughly 1.6449. The sum of the series up to the 4th term is 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, which is roughly 1.4236. If we subtract the infinite sum of the series and the sum up to the 4th term, we get the difference of 0.2213, which is less than 1/4, proving that our error bound was correct. The problem with finding the absolute error is that we need to be able to determine the exact value of the function we're approximating. Without knowing the true value that we're approximating, the maximum error bound can still be found using the Lagrange error bound formula. R represents the remainder of the error, x represents the given x value, a represents where the polynomial is centered, n represents the degree of the polynomial, and the n plus 1th degree derivative of f, where z represents some value between a and x. The remainder, r of x, is the Lagrange form of the remainder, and bounds on r of x found using this form are called Lagrange error bounds. The Lagrange error bound of a Taylor polynomial gives the worst case scenario for the difference between the estimated value of the function as provided by the Taylor polynomial and the actual value of the function. Let's approximate sine 2 using the 5th order Taylor polynomial and find the maximum error using Lagrange error formula. With this info, we already know that a equals 0, x equals 2, and n equals 5 to plug into the formula later. We first need to find the 5th order Taylor polynomial of sine x. After laying out the coefficients for the Taylor polynomial, we can find a sub 0 by plugging in 0 for f of x, a sub 1 equals 1 after finding f prime of 0, a sub 2 equals 0 after finding f double prime of 0, a sub 3 equals negative 1 over 3 factorial after finding f triple prime of 0, a sub 4 equals 0 after finding the 4th derivative at 0, and a sub 5 equals 1 over 5 factorial after finding the 5th derivative at 0. We also find the 6th derivative because we need the n plus 1th derivative of f, where n equals 5. Now that we found our coefficients, we can write our 5th order Taylor polynomial for sine x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. This is a graphical representation of the difference between the actual function sine of x and our Taylor series approximation x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Notice how as the graph moves away from 0, the less accurate the approximation is. At x equals 2, the distance between the two green dots is the exact error of the approximation of sine 2. With the fifth order Taylor polynomial, we can approximate the value of sine 2, which works out to be 2 minus 2 cubed over 3 factorial plus 2 to the fifth over 5 factorial, which roughly equals 0.933. Bringing up the Lagrange error formula again, we have everything we need to substitute the variables into the equation and find the Lagrange error bound. We know that a equals 0, x equals 2, n equals 5, and the sixth derivative of f is negative sine x. Our z value needs to be between 0 and 2 and maximize the error bound. Because the sixth derivative of f is negative sine x, substituting 2 for z will maximize its absolute value. With everything substituted in, the Lagrange error bound works out to be less than or equal to 0.081. We can find the exact error to verify that it's within the error bound. The exact error equals 0.024, which is less than 0.081. I'll be now talking about some of the applications of the Taylor series. As mentioned in the previous section, the significant meaning of Taylor series is that we can now express given functions in the form of a polynomial. It's often hard to evaluate complicated definite integral functions that are used to describe a system. This world is mathematically complicated. When you analyze the forces on an aircraft as it flies through the air or the stresses through a building that is subject to an earthquake, it turns out the equations are not only very difficult to solve, but they're often impossible to solve. Often, there's no analytical method to find these things, but engineers and scientists still need these solutions. Equations that describe real-world things are often differential or partial differential equations, which is why we simplify the differential functions into linear or quadratic functions that are easy to calculate using Taylor series. Going back to the Taylor series of sine x, a very commonly used Taylor approximation is sine x being equal to x for x values very close to 0. The first degree Taylor polynomial centered at x equals 0 for sine x is x. This is why it only works for values close to 0. The graph gives a visual representation of the domain at which the approximation is accurate. This approximation can be used for very small angles to describe the motion of a simple pendulum. The equation for the motion of a pendulum is d squared theta over dt squared equals negative g over L sine theta, which can be very difficult to solve. For very small angles of theta, we can approximate and use d squared theta over dt squared equals negative g over L theta instead. Some accuracy is sacrificed to get to a much simpler equation to work with. Another trigonomic Taylor approximation that is used is tangent x equals x for values of x very close to 0. The first degree Taylor polynomial centered at x equals 0 for tangent x is also x.
Alright, we're going to talk about application of Taylor series in statistics. For students who took AB Statistics with Mr. Cheyenne and Statistics with Mr. Buddha, you are familiar with this graph here. Along with the concept of normal distribution. Which is described by normal curve. So, normal distribution is a special pattern of a population which composed of individuals. Individuals form the population. So, if a population of a certain variable x is said to be follow normal distribution, what it means is that in this population, there you can find a value x equal mu, or we said mu is basically mean and average. We say there's a largest percentage of the population of which the individual has their x equal to average value, and as they go to the two extreme, it decreases. So let's put it in an example. Let's say the height of American adult in 2021, and we say that the average height is 1.7 meters, and toward the extreme where it would become x to 2 meters, x to the 1 meter, the percentage decrease, right? Okay. So I think up to now we have a pretty good understanding of the concept of normal distribution. Let's move on. So statistic is the sub-branch of mathematics, which means it has to be described by some kind of formula, right, about the normal curve. So let me introduce you to this. Let me enlarge this a little bit. Okay. So this thing here is called, it's called a probability density function, or in short, PDF. Okay, so now notice something interesting about this function here. It has a variable and has two constants that we need to set in advance. So we already know these things. This is the mean, the average. But what is this? So this is called variance in statistics, and the symbol, actually pronounced sigma, is the standard deviation. Standard deviation of the population, to be exact. But to speak in mathematical language, this is xi, which means the individual variable, minus the average of the population. This is the standard deviation. Okay, so without diving deeper to the concept of standard deviations, let's move on. And so if you were to try to plug this function inside a Cartesian system, which only have two variables, we need to assign value to these two constants. And let's make some assumption to make our life easier. So we do assume mu is 0 and sigma is 1, which make the variance also 1. Okay, now with this, let's give us some space here. Let's move this part to this part. Okay, now we simplify into this function. 1 over square root of 2 pi times e to the negative x squared over 2. Okay, now if you try to plug these things in a TI-84 or in the decimals, what you will find is this. Mark this x-axis and y-axis. You will find, let me graph that again. You will find this really similar, right? And it's centered at 0. Okay, now the x-axis, as we discussed before, represent the variable we're observing. Now y is the percentage of a given x in the population. So let's say if this point is 1, if you map it above, it's f of 1. Now this statement, probability of x equal 1 in this population is equal to f of 1. But actually that is not true in statistics. A simple explanation of that will be x is range from negative infinity to positive infinity, all real number inside this range. Or in another term, in the statistic term, it's called continuous variable. Now, in probability theory, we have this axiom that said all probability should sum up to 1. Now, if we do split up the probability of 1 to infinite x variable, the result is 0, which means the probability of x equal 1 is in theory 0. So that statement doesn't quite work out, isn't it? But what we can do is we can claim the probability within a given range is a real number that we can find. So now let's say in this example we will use 0.5 and 1. Okay, so 0.5, next 0.5. Now we don't really care about the two variable here, the two f of 1 and f negative 0.5. What we want to find is what's in between. In another word, we need to do integration of this function here. So now we write this as negative 0.5, 1 to the exact function we were writing before, dx. think it would be better if we find a more general form of this equation. So let's find the indefinite integral of this function. And we took the constant out, as always. Okay, now let's stop for a second. Let's think. Let's suppose there's this imaginary decision tree that pops out in your mind, as you might have when you're solving integration of functions. You might want to try usub first. Try usub, then you try tricksub, and then you go on to Slater, and you go on to Google. Now, I'm just kidding there. If you did try out the 2 previous branch of the decision tree, what you might find is a dead end. You might find it tedious or even impossible to solve. So what I'm going to do today is to introduce a new branch to your decision tree. We will try to solve these things with Taylor series or find approximation to the result. Okay? Now, from the previous section of the video, my partner Daniel talked about how to express this function in form of Taylor series. That's this. Okay, now I hope you still remember this microwave method, where where there is x, we plug in the variation of the x squared that we have, so we end up something like this. Okay, so now let's plug it back. Okay, and there's this operation of integrating the whole Taylor series that we do near the end of the semester. Let's do this. Yeah, remember that actually this things here is a constant, so that means there's no need to integrate them. Actually, before that, let's move a step backward. Let's write it in a clearer form to help us. We'll write it in this way. Okay. Now, let's do the integration. Now everything is the same, the constant part, but this part we do x to 2n plus 1 and move 2n plus 1 down. Okay, now here we have the indefinite form. Oh, actually, nope. Now we have the indefinite integral form. Okay, let's put it in a more user-friendly way, shall we? So what we do is p a x, so x is within a and b, and then we write 1 with b and a. Now this is the one you can use directly. Okay, so I calculate these things on my TI-84 to give an example. Sorry. Okay. Nope. Okay, actually let's just zoom in there. Okay, so notice that due to the limitation of TI-84, I cannot simulate the infinite term here. and that's why I replace it with a variable called w. And as w approach infinity, the accuracy will increase. But in this case, I set it to 50. All right, and then I can see I plug in the variable. I assign these things to L, representing lower bound, and the other one to U, representing upper bound. And then I get the result here. And this might be confused for people who didn't take statistics class, but those who did should be familiar with this command, normal CDF, which is a built-in function to find the area under a normal curve. And you can see the result is pretty close, okay? Now, I did prepare a hand-on example, or a more real-life example for the audience. So let's say there is rumor that the distribution of student score in a STEM class in this school follow the normal distribution with a mean of 70 and a standard deviation of 15. If a score of 50 is considered a fail in this class, what's the percentage pass rate in this class? Okay, so up to now you should be confused because the mean is 70, it's centered at 70. And that isn't quite the case we are dealing with before with the simple assumption of the normal curve centering at 0. And that's where the z-score come in, or called the standardized score. What it basically do is that it map any given data set, in this case a data set with a mean of 70 or standard at 70. We use this to convert it to a data set with its center at 0. And the formula for the z-score is this. So hopefully after you did that, you should be convert 70. You should convert all this number here and map it into a system with it centered at 0. And yeah, so you're welcome to try out and try to calculate what's the percentage pass rate in this class. And if you're interested in the z-score and the reasoning behind why we can make such assumption with the normal distribution, you're welcome to take AP Statistics. But above will be all the content of our presentation of our group. So thank you for watching.